Now we are discussing about law of magnetism. Let's start the session. Law of magnetism. It explains how magnetic materials respond when we apply a magnetic field. The first point, when an external field applied to ferromagnetic materials like iron, cobalt, nickel are made up of small regions called magnetic domains. Each domains act like a tiny magnet. So with its own north pole and south pole, that means positive and negative ends. In an unmagnetized material, these domains are oriented randomly, so their magnetic effects cancel each other out. When we apply an external magnetic field, the domains start to rotate and align parallel to the field direction. This alignment makes the overall magnetic field of the material much stronger. The next point is domains are larger than atoms but still very small. A magnetic domain contains billions of atoms are aligned together. While they are far larger than single atoms, they are still microscopic, meaning we can't see them without special instruments. The next one is alignment increases magnetic flux density due to atomic interactions. As more domains align, the material's ability to carry magnetic lines of force called magnetic flux density it increases. That means the number of lines is how many number of lines are in the magnetic field. This is the magnetic flux density. So the flux density is equal to the line of force. This happens due to atomic interaction and the cooperative behavior of aligned domains. The next is Barkhausen effects. Domain alignment doesn't happen smoothly. It happens small, sudden jumps as domain walls move and reoriented. These jumps create small and measurable changes in magnetism called the Barkhausen effect. While the special equipment we can detect these jumps, and sometimes this effect is used in material testing to study the stress or structural changes. The next point is magnetic saturation. There is a limit to how much a material can be magnetized. The magnetic saturation is the point where all domains are aligned in same direction. No further increase in magnetism is possible, even if we increase the applied magnetic field. At this stage, the material has reached its maximum magnetic potential. So the next slide is the materials influenced by magnetic fields. Here the different materials react differently when placed in magnetic field. This reaction depend on their atomic structure and magnetic permeability. First we saw the paramagnetic materials. So the paramagnetic materials are weakly attracted to the magnets. Magnetic permeability is only slightly greater than air. Okay, what is permeability? Permeability is one measurement of how easily a material can allow magnetic lines of force to pass through it. This is the permeability. A material with high permeability lets magnetic fields pass through it easily. It becomes strongly magnetized. A material with low permeability resists magnetic field penetration and it doesn't get strongly magnetized. This effect is so small that these materials are not suitable for magnetic particle testing. So paramagnetic materials are not suitable. Example, aluminium, platinum, manganese, magnesium. The next one is ferromagnetic materials. These are strongly attracted to magnets and they have high magnetic permeability. It can carry a lot of magnetic flux. These are the only materials suitable for magnetic particle testing. Example, nickel, iron, cobalt. Their magnetic domains can align easily and creating strong magnetic fields and clear defect indications. The next one is diamagnetic material, weakly repelled by magnetic fields. Magnetic permeability is slightly less than air. It not used in magnetic particle testing but can be useful in specialized applications such as detecting hidden conductors in some testing setups. Example, copper and bismuth. This is the best examples for diamagnetic materials. Next one is non-ferromagnetic materials. Neither strongly attracted nor repelled by magnets. They have low magnetic permeability, so magnetic fields pass through them without much interaction. It includes most metals like stainless steels, the grade 304, 316, and most non-metals also. Non-metals like glass, plastics, ceramics, these are non-metals. The next one is not suitable for magnetic particle testing. And the alternative methods, or if the material is non-porous, we can use liquid penetrate testing instead of magnetic particle testing. If you try to use magnetic particle testing on aluminum, you won't see any defect indications because the material does not hold a magnetic field. That's why we must first check if the component is ferromagnetic before planning a magnetic particle testing inspection. Next, we see the characteristics of magnetic fields. The first one is magnetic polarity. Every magnet has two poles, that is north and south pole. This is true for bar magnets and horseshoe magnets and even broken magnets also. If one bar magnet is broken, it's not a damaged. It creates a new magnets, like this is a new pole, south and north. Each piece will still have both poles. This is the magnetic polarity. Next one is magnetic flux patterns. The magnetic field around a magnet can be shown by placing iron fillings on paper over the magnet. The fillings arrange themselves into curved lines. These are called lines of force or magnetic flux lines. These are flux lines or lines of force. Then properties of lines of force. First, do not cross each other. They always run in smooth and continuous curves. The next one is follow the path of least magnetic resistance. They travel more easily through magnetic materials than through air. The next one are most densely packed at the poles. The magnetic field is strongest at the north and south poles. Next, flow directions. Outside of the magnet, the lines go from north pole to south pole, and inside the magnet the lines are flow south pole to north pole. The next point is do not enter or leave at the center. The lines always emerge from poles, not from the middle of the magnet. The first one is straight bar. This is a horseshoe magnet. The magnet has two poles, north pole and south pole. The positions are closed. The magnetic field lines leave the north pole. The curve through the air. This is low reluctance path and enter to the south pole. When the ferromagnetic object like a nail is placed near the poles, this is the near the poles, the magnetic field flows through the nail, magnetizing it temporarily. The nail is then attracted toward the magnet due to the interaction of its induced poles with the magnetic poles. This setup produces a strong lifting and pulling force. Because the poles are close, the field is concentrated. The next one is magnetized ring. This is the magnetized ring. This is ring magnetized. A is a horseshoe magnet. This is a magnetized ring. In this configuration, the magnetized ring has its magnetic field completely contained within the material. The magnetic lines of force travel in closed loop inside the ring. No external leakage. Because there are no external poles, the magnet cannot attract external ferromagnetic objects or magnetic particles. This is a situation where a component can be magnetized but shows no visible magnetic effect on the outside. Third one is broken magnet. When the ring magnet is broken or damaged, the closed loop magnet circuit is interpreted. At the break, north and south poles forms. The magnetic flux leaks out into the surrounding air. This leakage field behaves like a regular magnetic poles, and magnetic particles or ferromagnetic materials will be attracted to the break area. In magnetic particle testing, leakage field is what make defects visible. Just like the break in the magnet creates the visible poles, leakage fields at discontinuities or make defects visible. In MPT, a defect in a part acts like a break in figure C. The defect interrupts the magnetic field, causing leakage, and which attracts magnetic particles and makes the flaw visible. Thank you. We will see the next video.